Hey everyone, welcome back to Econ 145 Bootcamp. Today we are going to talk a little bit about your regression results. And this is the results you get from your statistical software package. There are tons of software packages. They all do approximately the same thing. They try to estimate the relationship between your variables, right? Estimate the causal relationship between your independent variables and your dependent variables. So I'm going to pull up a couple of different regression results tables, and we'll talk about how we can interpret them, how they are different, what we can expect from them, and some of the stuff in there. So hopefully that sounds interesting to you. This is stuff you should have covered in 140, definitely 141, but we don't really have time to cover it in 145, maybe a brief review. And so if it's something you're not comfortable with, it's nice to have a reference. Ideally, you've got your notes or your textbook from 140 from your econometric class. But if you don't, it happens. Let's do a review of it. Okay, sounds good? All right, let me go pull up some regression tables for us. Here we have our first set of regression results. This is a regression table from Stata, and you can see here I have my commands. The command in Stata for a regression is just reg, and then your y variable, in this case, sale price of a home, and then your x variable. So I have the lot size of the home, the bedrooms, the number of bedrooms, the number of bathrooms, and the air conditioner, and whether or not a house has an air conditioner or not. And it's going to be vitally important to understand and interpret your results. You have to keep track of what your variables mean and how they are measured. So in this case, I'm just going to go ahead and make notes about this. Sale price is in dollars. Lot size is in square feet. Bedroom is the number of bedrooms. Bathroom is the number of bathrooms. And air conditioner is what's called a dummy or a binary variable, where it's 1 if there's an air conditioning system and 0 if there's not. And I need to know all of that in order to interpret my coefficients. So we want to remember what we're talking about here is we're talking about a regression equation where we have y equals a constant, usually alpha, plus a coefficient for every explanatory or independent variable. So in this case, I have, oops, my alpha looks weird. I have my y is sale price, right? It's how much is the house going to be sold for. And it's a function of the size of the lot size, the number of bedrooms, the number of bathrooms, and whether there's an air conditioner or not. And I have the x values for each observation. I have a sample here with, and you can see it on the regression results. It'll always tell you number of observations, 546. So out of 546 houses, I have their sale price, lot size, number of bedrooms, number of bathrooms, and air conditioning. And so there's a y, x1, x2, x3, x4 for each observation. And then the statistical software looks at all of those variables, all of those examples of a y and an x and an x and all the other x's, and then goes through and estimates what the beta and alpha are, what the constant is, and what the coefficients are. So there's a coefficient for x1, there's a coefficient for x2, and that's telling us the magnitude or the size and direction of the effect lot size, bedrooms, bathrooms, and air conditioning have on sale price. So if we look here in this regression table, it's all labeled, but if you don't remember what the labels are, it can be a little intimidating. So let's go through and we'll look first at sale price being our y, and then lot size is our first x. And the first number here is our coefficient. And so the coefficient is that first beta 1, and it is 4.76. 4.76. I'm going to round to that because that's good enough. And so that tells me that if x is measured in square feet of lot size and y is measured in dollars of sale price, then each additional square foot of lot size is going to tend to increase sale price by $4.76 or $4.76. Does that make sense? So if x goes up by 1, y goes up by 4.76. And we can do this in another way to make it make even more sense. So let's say we have a house with some given sale price. Let's say we have a house that's it's California, so we're going to say it's a $400 house. And every house on that lot has 1,000 square feet, but one house has 1,001 square feet. We're going to expect that the house with 1,001 square feet is going to not be $400,000, but it's going to be $400,000 and $4.76. That each additional square foot is going to tend, not always, because we're not 100% certain on this, but it's going to tend to increase the sale price by $4.76. So if we add another square foot, now it's going to be $9.52, or 4.76 times 2. Does that make sense? Kind of, hopefully. If not, hit me up, let me know, and we'll talk about it some more. But then we have these other things here. And remember when I said we're not 100% sure about that coefficient, the marginal effect of a change in lot size on house price? Well, these other numbers here tell us about our certainty. And so when we estimate this beta 1, we are not sure what the real value is. And so we put a hat on it because it's an estimate. And what we really say is that that estimate, that beta 1 hat, is actually somewhere in a range. And we call that range the confidence interval. Within that confidence interval, we're pretty sure this value rests. The statistical software calculates the confidence interval for you, and it tells you how certain we are. If you look here on the regression results, you can see 95% confidence interval. And the numbers here, 4.04487 and 5.481321, that's our confidence interval. It's the lower and upper bound range within which we are 95% confident that our actual true real value of beta exists. So beta hat 1 is somewhere in between 4.04, I'm going to round again, and 5.48. We don't know the true value of beta 1, but we are pretty sure it's somewhere in here. That value, 4.76, lies within that confidence interval. And that is to be expected because the statistical software is calculating all of these at the same time using the same formulas, calculations, and variables. And hopefully in your 145 class, they would have gone through and talked to you about how to calculate those. I am not going to do that here. If you have more questions, you can always reach out to me, reach out to another professor, or check out my Econ 140 videos. So one of the ways we can tell how confident we are about this estimate is by how big that confidence interval is. The bigger it is, the less confident we are in our estimate. The smaller the interval, the better we are. But there's other ways we can tell too, and those are going to be our tests of statistical significance. And that's going to be this number right here, which is our standard error, this number here, which is our t-statistic or test statistic, and then our p-value here. And the p-value is the probability that the absolute value of the test statistic is high enough to reject the null hypothesis. What? Remember, we're doing all of this. This is statistical analysis. And so what we're trying to do is estimate beta hat, which we did. We also want to test whether it's a very accurate estimate. The confidence interval tells us that, but so does the test stat and the p-value. If the p-value is low and the t-stat is high, we're in good shape. For a 95% confidence interval, we want a t-stat below 0.05. That's the general rule we use. Here we can see the t-stat is 13.03 and the p-value is 0.00. Other statistical software will give you a more precise p-value. Stata tends to pretty much round to those three decimal places. And so you get a lot of zeros, but that's good. That tells us that we are very confident. We are 95% confident that this is an accurate estimate of the true value, the true effect of lot size on home sale price. We can also tell here by the standard error. In this case, the standard error is 0.36. And so a way to think about that is, if we go back, I'm going to use this whiteboard one more time, where I'm estimating the beta for lot size, and we have this value for the beta for lot size of 4.763 or 4.76. That's our what's called point estimate. And we're pretty sure that it's that point. We are 95% confident it lies within our confidence interval, 4.04 to 5.48. But we can also say that we have a standard error, and the error is sort of our margin of error in either direction. And so we're saying plus, let's put this the other way so it makes sense, plus or minus 0.3, let's see, that's 3.6. I'm going to round it up to 3.66, and plus 0.366. That point estimate, we are pretty sure that's the accurate beta hat with a margin of error of our standard error, 0.366 or 0.3656 on either side. Does that kind of make sense? We want our standard error to be small. How small? Smaller than half of our coefficient. If we think that the effective lot size on home sale price is $4.76, we want our margin of error, our standard error, to be less than $2. Because if I come through and I say, oh, well, I think the effective lot size on sale price is $4.76 plus or minus $10, I am not happy, right? If I say it's $4, give or take $10, that's a pretty crummy estimate. And so that's what we want to think about. So we want to look at our coefficients and test them for statistical significance. We want small standard errors, large t-stats, and small p-values. Those things are all going to go together. So very, very rarely, I don't think it's even possible to have one of them be statistically significant and the other not. As they go to being borderline, they'll do it together. Same for the confidence interval. The confidence interval tells us how confident we are, and you can change that with your statistical software, but how confident we are that it fits within a given range and what that range is. The broader the range, the more confident we are we're in it, but that's a lot more variability. And then we want to interpret our regression results by saying, okay, well, a marginal change in our X, in this case lot size, is going to have a beta hat effect on Y, sale price. So each additional unit of lot size is going to tend to increase sale price by $4.76. If we look at the next row, we have bedrooms. Each additional bedroom is going to also have a positive effect on sale price because these are positive coefficients. And that makes sense, right? An extra bedroom is going to increase the value of a home. What's the effect on sale price? One extra bedroom raises the sale price by approximately, or tends to raise the sale price by $4,914.64, give or take. Are we certain about that? We're pretty certain. We're 95% confident, right? We can accept this estimate at the 95% confidence interval and at the 5% significance level. And so you can go through and interpret all these coefficients. Here's the last one, air conditioner. That's a binary, right? That's a dummy variable. You don't have a number of air conditioning units. You either have central air or you don't. Sacramento County, it's a really big deal to have central air. So having air conditioning is going to tend to increase, again, Y, our sale price, by $16,237.69. If you take that air conditioner away, you're going to tend to reduce sale price by $16,238, give or take. Hopefully that makes sense. So that's how we would interpret our coefficients, their statistical significance. Remember, when we're looking at our X, whatever our X is, you need to know what the units are so that you can talk about how a 1 unit change in X has a beta hat-sized effect on Y, and that's going to be in the units for Y. So if you're looking at the effect of bathrooms on sale price, it's going to be an extra bathroom changes sale price by $18,000. If you're looking at the effect of a years of education on wages, each additional year of education is going to have a beta hat-sized effect on the dollars a person earns on their wages. Does that kind of make sense? Other things we can look at here, the next biggest thing we want to look at is our R squared. And our R squared right here is our measure of the value of the model. So everything in this box here, all about the coefficients. Each coefficient has a standard error, a t-stat, a p-value, and a confidence interval. Up here, these measures, this top half, it's all about the model. So not just one beta, but the entire model that we're looking at, where we're saying, okay, Y, or lot size, is equal to alpha plus beta 1x plus beta 2x plus beta 3x, and I have 4 plus beta 4x plus some error term, where Y is lot size, X1 is, Y is sale price, X1 is lot size, X2 is bedrooms, X3 is bathrooms, and X4 is air conditioning. In this case, we go through, and so each X has its own beta and its own statistical significance. When we look at this top half, we're looking at the whole model. And that says this is the machine, right, the model that explains variation in Y. And so the R squared is a measure of the validity of the model. So our R squared tells us how much the model tends to explain changes in Y. It can be anywhere between 0 and 1. 0 is improbable, and 1 is pretty dang impossible because we can't measure everything. There are stuff we can't account for. Can you predict a house's sale price based on lot size, bedrooms, bathrooms, and air conditioning? Sure, but there's other stuff that matters, and some of that stuff might be difficult to measure. Curb appeal, neighborhood value, time period, all are going to have an effect. So this model explains some variation in sale price. Our R squared tells us it actually explains 56%. So our R squared tells us that this model tends to explain 56% of the variation in sale price of a home. The adjusted R squared is another measure that takes into consideration the size of the model, how many variables you're using. And then over here, this is the regression sum of squares, the residual sum of squares, and then the total sum of squares gives you another measure of the validity. This is how these numbers here on this side are how we calculate the R squared, and using the degrees of freedom, the adjusted R squared. The last part over here I'm going to talk about is your F statistic and the p-value for your F statistic. Just like we had a t-stat and a p-value to test the null hypothesis that our beta, our coefficient, was significant, we do the same thing over here. We want a small p-value and a large f-stat to tell us our model has explanatory power. It is statistically significant. If the f-stat is large, which this one is, then our p-value will be small. We want a p-value below 0.5 or 0.05 in order to be very confident that our model explains some variation in Y. That tells us that our model is significant and explains variation in Y at the 5% significance level. So that is a quick overview in how to read a results table, how to look at interpreting your coefficients, your statistical significance, and your R squared. If you don't use Stata, what you'll find is really, really similar stuff. So I'm going to open the exact same data set, but in Excel, and you'll see that you get pretty much the exact same, oops, wrong place, pretty much the exact same regression table, just organized a little bit differently. And so whatever software you're using, you're going to always get an estimated coefficient, a standard error, a t-stat, and a p-value, and a confidence interval for every explanatory variable. So here's that data set, and you can see I have lot size is my first x, sale price is my y, number of bedrooms, number of bathrooms. There's other y's here I'm not going to use, so I'm just going to get rid of those. And then I'm going to get rid of garage and desired location too. More variables I'm not using. So now I have my sale price, which is my y, and then my 3 x's, which are my model that I'm trying to use to explain variation in sale price. To run a regression, I go over to data, and then, oops, let's get this opened up. You might not have this in your Excel, you might have to download it, but you want to use the data analysis tool regression, and that will let you run a regression. You select your y variables, which is going to be this one, and then you select your x variables, which are going to be all of these. And then if I want to label them, I can set my confidence interval. I'm going to use the default of a 95% confidence interval, but I'm also going to add in 99% confidence interval. And I'm going to tell it to put all of my regression results right here so I can read them. And then I go back and run the regression. Whoop. Okay, sorry I haven't run a regression in Excel for a while. I'll probably try to delete this out, but the basic idea here is that you do have to put, you can't have just select the whole column. I have, 500 variables, give or take, and so Stata or Excel wants me to say what the end value is. So it's going to be from A02 to A547, and then I can do the same thing over here. There we go. If you want to learn how to run regressions in Excel, that's a whole other video that I'm happy to show you, but it's not the best tool. There are better tools to use. Okay. So now if we go back up, there's my regression results table. So this is a standard regression results table from Excel. I like to make it a little bit bigger because it's a little bit cramped here. But you can see you get some of the same stuff. So here we have, oops, the intercept, the alpha, right, the constant. Here are my 4 x's. They each have a coefficient. So let's see, lot size has a coefficient, a standard error, a t-stat, a p-value, upper bound and lower bound at the 95% confidence interval, and then I also added in the 99% confidence interval. So that's saying, okay, I'm 95% certain it's between 4.04 and 5.5, but I'm 99% confident that it's between 3.8 and 5.7. So the more confident I am, the bigger the range is going to have to be. Up here I have my degrees of freedom, I have my total number of observations, I have my sum of squares and residual sum of squares and regression sum of squares that can help me calculate my R squared. And then up here I have my R squared and my adjusted R squared. And then I have my F-stat and the p-value for my F-stat. So all the same stuff that I had somewhere else, in the Stata Excel or the Stata regression result, I have in the Excel regression result. So I can again interpret this and say, okay, well, each additional bathroom is going to tend to increase lot size, or sorry guys, each additional bathroom is going to tend to increase sale price by $18,000. Each additional bedroom is going to tend to increase sale price by $4,914, and so on. Other software are going to have similar tables. It's going to have the same stuff. It just might be labeled a little bit differently, organized a little bit differently, but it's always going to have that same stuff. So hopefully that was a fun little refresher into how to read regression results, how to interpret them. You want to remember you need to, in your 145 paper, you have to interpret those coefficients. You want to talk about your statistical significance. You want to talk about your R squared and its statistical significance. And you want to be able to interpret these things because that's the whole point, right? That's what we're trying to do, is measure the effect of our explanatory variables on our variable of interest. Regardless of what software you use, the interpretation of the coefficients and their statistical significance measures are going to be based on your variables, your values, their units, that kind of stuff, not on what statistical software you use. So it really doesn't matter what software you use. The interpretation is based on your data. So hopefully that helps. Let me know what questions you have, and I'll see you next time. Thanks so much.